Okay, so get this. Today, we're doing a deep dive on Euler's totient function.
Euler's totient function, huh?
Yeah, and I know what you're thinking.
What am I thinking?
Sounds kind of boring, right? Like, how exciting can counting numbers really be?
You got me there. Sometimes math can sound about as thrilling as watching paint dry.
Exactly. But trust me on this one, this function is way cooler than its name lets on.
Okay, I'm intrigued. I'm in. Tell me more. What makes it so special?
Well, we're going deep on this. We've got excerpts from the Online Encyclopedia of Integer Sequences.
OEIS, right?
You got OEIS, and we've also got the Wikipedia page, so you know we're going to cover some serious ground here.
All right, so what is this Euler's totient function? What does it actually do? What's the deal with it?
So the OEIS kicks things off by saying it's all about counting numbers less than n that are, get this, relatively prime to n.
Relatively prime. Now we're just throwing out fancy math terms.
I know, right? It's like we need a whole glossary just to understand the definition.
Yeah, seriously. So let's break it down. What does relatively prime even mean?
Okay, so basically, two numbers are relatively prime if the only number that divides into both of them is 1.
Okay, so they don't share any other common divisors, just one.
Exactly. So, like, if you take 12, you've got 1, 2, 3, 4, 6, and 12 as divisors.
Right, all the numbers that divide evenly into 12.
Yep, but only 1, 5, 7, and 11 are relatively prime to 12.
Because they don't share any of those other factors.
Exactly.
Ah, I see. So it's about finding those numbers that are kind of independent. They don't have any common baggage with our starting number.
Yes. That's a great way to put it. And the totient function, which is written using the Greek letter phi,
Phi.
or upsilon, it tells you how many of those independent numbers are left, how many are relatively prime to n.
So for our example with 12,
Hmm?
12 would be 4, right? Because we found 4 numbers that were relatively prime to 12.
You got it. 4 is the magic number. But here's where it gets really interesting.
Okay, hit me with it. What's this magic number got to do with anything?
You're telling me this has something to do with shapes?
Shapes, like geometry.
You read my mind. We're talking polygons,
Really?
specifically.
Polygons like triangles, squares, pentagons, that sort of thing.
Exactly. You see, there was this brilliant mathematician named Gauss, and he proved something really cool.
All right, what did Gauss discover?
He proved that you can draw a perfect polygon, with all equal sides and angles.
Yeah.
Using just a straight edge and a compass IF, and this is a big IF, the number of sides of that polygon has a totient that's a power of 2.
Whoa, hold on. So you're telling me this function, this thing about relatively prime numbers, can tell us if we can draw like a perfect pentagon or hexagon or something just using those basic tools?
You got it. Isn't that wild?
That's crazy. I mean, how does that even work?
That's a great question, and to be honest, it's a bit complicated to explain quickly.
Oh, come on, you're killing me.
But the gist is there's this hidden connection between the factors of a number
Okay.
and the angles you can create when you divide a circle.
Angles in the circle. Got it.
And it turns out that being able to construct certain polygons, it all comes down to being able to divide a circle into those specific angles using just a straight edge and compass.
So, like, some angles are easier to make than others if you only have those tools?
Exactly. And Euler's totient function, it's like the secret code that tells us which angles are possible.
That's wild. I never would have guessed that there was a connection between this relatively prime number stuff and something like drawing shapes with a compass and straight edge.
Right. It's like these totally different areas of math are secretly talking to each other.
Exactly.
Yeah.
It's mind-blowing.
Okay.
But let's take it back to the totient function itself,
Okay, yeah, let's rein it in a bit.
because we don't want to be stuck counting relatively prime numbers one by one for the rest of our lives, right?
Can you imagine if we had to do that for like a giant number? It would take forever.
Talk about tedious. There's got to be a better way, right?
There is, thankfully. And it's called Euler's product formula.
Euler's product formula. Okay, sounds fancy.
It's a lifesaver, I'll tell you that much.
So how does it work?
Okay, so you take your number n.
Right, our starting number.
Yep. And you multiply it by a series of fractions, and each fraction is 1p.
1p. Okay, but what's p?
Ah, that's the key. P represents each distinct prime number that divides n.
So we need to know the prime factors of our number.
You got it. Let's say we have 20.
Okay, 20.
What are our prime factors?
Let's see, 2 and 5, right?
Exactly. So we do 20 times 112 times 115.
And that gives us 8, which is the totient of 20, right?
Boom! You nailed it. Way faster than listing out all the numbers less than 20 and figuring out which ones are relatively prime.
Right. This formula is like magic. It just spits out the answer.
It's pretty slick, right? Like, this formula has a sixth sense for prime numbers or
It's
something.
like it knows exactly which numbers to sift out.
Exactly. And the best part, this is just the tip of the iceberg.
Seriously, there's more.
Oh yeah, we haven't even touched on the connection between Euler's totient function and pi.
Pi. You're messing with me, right? Prime numbers, shapes, A and D pi.
I'm telling you, this function is full of surprises. But we'll save that for after the break. Pi and the totient function. Where do we even start with that?
It's pretty wild, right? Like, what could this function possibly have to do with pi?
Okay, so the OEIS mentions something about adding up all the totient values. Like if you calculate phi for all the numbers from 1 up to some number n.
Right. Adding up all those totents.
Exactly. And get this, the result is supposedly close to a formula that involves pi squared. Pi squared? Can you believe that?
Wait, seriously. So we're talking about this function that counts relatively prime numbers.
Mm-hmm.
And somehow it knows about pi, this constant that shows up everywhere in math, like circles, trigonometry, probability, you name it.
It's crazy, right? Like, what's the connection?
Well, there's this proof, and it's a bit involved, but it basically uses the totient function to show how the distribution of prime numbers is related to the area of a circle.
Hold on, slow down for a second. Are you saying that prime numbers, those building blocks of numbers, somehow have a connection to circles through this totient thing?
It's like these tiny prime numbers are holding secret information about circles, and the totient function is the key to unlocking it.
You're blowing my mind right now, I gotta be honest. This is why I love math. You find these hidden connections between things that seem totally unrelated.
It's the best, right?
But okay, let's switch gears for a second. We were talking about cryptography earlier. You mentioned that Euler's totient function plays a role in our digital lives, and I'm dying to know how.
Oh, yeah, that's right. So remember how the totient function helps us find those relatively prime numbers?
Yeah, those independent ones, right?
Exactly.
Huh.
Well, that property is actually super important for something called RSA encryption.
RSA encryption. Okay, I've heard of it, but I'll be honest, I'm a little fuzzy on the details.
That's right. It's basically a way to send secret messages online.
Okay, so like how does it work?
So imagine you want to send a secret message to someone.
Okay.
With RSA, you use a public key to scramble the message so no one else can read it.
All right, so anyone can see this scrambled message.
Yeah, but here's the catch. Only the person you sent it to, the receiver, they have a special private key that can unscramble the message.
Okay, I see. So it's like a lock and key, but digital.
Exactly. And guess what plays a key role in generating these public and private keys?
Don't tell me it's the totient function.
You got it. Euler's totient function is like the secret ingredient in this whole encryption process.
No way. So those relatively prime numbers, they're what's keeping our online messages safe.
In a way, yes. The security of RSA encryption relies on this idea that it's really, really hard for computers to factor very large numbers, especially when those numbers are the product of two huge prime numbers.
Okay, I'm starting to see the connection here.
And remember, the totient function is all about those prime factors.
So if you could easily calculate the totient function for a massive number, you could crack the RSA code.
Exactly. But the thing is, finding those prime factors is incredibly difficult for computers, especially when we're talking about numbers with hundreds of digits. It's like trying to find a specific grain of sand on a beach.
Wow, so our online security is basically hanging on the fact that some math problems are just too hard to solve quickly. That's both comforting and a little scary at the same time.
Right. It's like this weird paradox. But hold on, there's even more to this story. Remember that whole thing about Han being divisible by any number Q as long as N is large enough?
Yeah, that seemed kind of random, to be honest.
Well, it turns out that this randomness is actually crucial for cryptography.
Really? How so?
It all comes down to unpredictability. If totient values were easy to predict, or if they clustered together in certain ways, hackers could exploit those patterns to break codes faster.
That makes sense. So this randomness throws a wrench in their plans.
Exactly. It's like adding an extra layer of security on top of the already difficult problem of factoring large numbers. And it all stems from those seemingly random properties of the totient function. Pretty cool, huh?
I'm speechless. We started with counting relatively prime numbers, and now we're talking about the foundations of online security. This Euler guy was really onto something.
Absolutely. But guess what? There's still more to explore. Did you know that those totient numbers, the outputs of the function, they have their own special name and a whole bunch of intriguing properties?
Seriously, this just keeps getting better and better.
I know, right? And we'll dive into that right after this.
So you were saying something about the outputs of Euler's totient function having their own special name.
They do. We call them totient numbers.
Totient numbers, catchy. So any number that can be the result of the totient function, that's a totient number.
You got it. Like, remember how we found that 10 equals 4?
Yeah,
That means 4 is a totient number. It's part of the club.
cool. So what's so special about these totient numbers? What makes them different?
Well, for one thing, not every number can be a totient number.
Wait, really? There are numbers out there that can't be produced by the totient function.
Yep. It turns out that any odd number greater than 1, you'll never find it as the output of Euler's totient function.
No way. So you're telling me that no matter how many numbers we plug into that formula, we'll never get an answer like 3, 5, 7, and so on. That's crazy. Why is that?
It's a bit complicated, but it has to do with how the totient function works with prime factors. Basically, because of the way those prime factors interact, the output will almost always be an even number.
Wow, that's mind-blowing. It's like this hidden rule in the number system that we'd never notice just by looking at the numbers themselves. We needed Euler's totient function to come along and reveal it. So, okay, we've got some numbers that can be totient numbers and some that can't. What else is there?
Well, there's this really cool concept called valency or sometimes multiplicity when it comes to totient numbers.
Valency. Okay, I'm listening. What's that all about?
Think of it this way. The valency of a totient number tells you how many different ways you can get that totient number as the output of the function.
Okay, so like we know 10 equals 4. To find the valency of 4, we'd need to see if there are any other numbers that also give us a 4 when we use them in the totient function.
Exactly. It's like asking how many different inputs to the function all lead to this same totient number as the output.
Ah, that makes sense. So are there totient numbers with a valency of like a million? Meaning there are a million different numbers that all give you the same output?
That's the thing. As far as we know, there are totient numbers with really, really high valencies. But here's the kicker. Mathematicians have never found a totient number with a valency of just 1.
Hold on, a valency of 1. So you mean a totient number that's only the output for one specific input, and they've never found a single one.
Not a single one. And what's even wilder is that no one has been able to prove whether or not such a totient number could even exist. It's an unsolved problem in number theory.
You're kidding. So there could be this whole class of unique totient numbers out there, each one paired with its own special input, just waiting for someone to discover them.
Exactly. And that's what makes this whole thing so fascinating. We start with this relatively simple idea, counting numbers that don't share divisors. And it leads to these incredibly deep, unanswered questions about the very nature of numbers.
I know, right? I have to admit, I thought this was going to be a tough one, all about dry formulas and boring calculations. But this has been an incredible journey. We've gone from counting relatively prime numbers to uncovering these hidden connections to geometry, cryptography, and now even unsolved mysteries in the world of numbers.
It just goes to show that math is full of surprises. You never know what you're going to find when you start digging deeper.
Absolutely. And who knows, maybe one of our listeners will be the one to crack the code on those unique totient numbers. But for now, we'll leave you with this thought. If Euler's totient function is all about the numbers that don't share divisors, what happens when you look at the numbers that do share divisors? What kind of patterns and surprises are hiding there? That's something to ponder, and we'll see you next time for another deep dive.